Good afternoon, ladies and gentlemen. Welcome to the Shaw Prize Lecture in Astronomy by Dr. Jean-Luc Chu, the Shaw Laureate in Astronomy 2018. May I first invite Professor Andrew Chan, head of Shaw College, to deliver his welcoming address. Professor Chan, please.
Hi. Bonjour. Dr. Jean-Luc Chu and Dr. Catherine Chu, according to the script, they haven't put down your name, so I have to check on your name very carefully. Distinguished guests, colleagues, students, ladies and gentlemen, good afternoon. On behalf of Shaw College, I would like to extend our warmest welcome to you to the Shaw Prize Lecture in Astronomy 2018. Our close association with Sir Run Shaw started in 1986. That's the year I joined Chinese University. So I'm one of the antique. When the college was founded, so when I came, Shaw College was born. So it's very easy for you to remember. And Sir Run became our patron. In later years, Sir Run resolved to devote his efforts to establish a masterpiece by the name of Shaw Prize. And in 2002, the establishment of the Shaw Prize was formally announced. Where? In the same venue where you are sitting. Time flies, and this year marked the 15th anniversary of the prize. And it is widely known the Shaw Prize is an international award to recognize imaginative individuals. So it's more than science. You have to have very artistic. You have to be a very good artist in order to come up with, in order to be given that particular prize, who have contributed to furthering not just science, but societal progress, enhancing the quality of life, though it's on astronomy or mathematics and all that. So at the end of the day, we are pointing at quality of life of mankind and enriching humanity's spiritual civilization. The Shaw Prize consists of 3 annual awards. First of all, astronomy, alphabetically, of course, and life sciences and medicine and mathematical sciences. This year, we have honored to invite Dr. Jean-Luc Chu to deliver this particular lecture. It's by rotation, not by selection, even by selection, we will select this one. We are also grateful to Professor Li Hua Bai. I don't know whether I pronounced that correctly. Hua is 中华的华, Bai is 白色的白. From the Department of Physics of CUHK. He would introduce Dr. Chu and moderate the Q&A sessions, so be nice to both of the two gentlemen. The college is deeply honored to have a common benefactor with the Shaw Prize, and we are also exceptionally delighted to have the opportunity to learn from the world's foremost scientists and great mind. May I now pass the time back to the MC? Thank you. Thank you is merci. Merci beaucoup.
Thank you, Professor Chan. May I now invite Professor Li Hua Bai from the Department of Physics, our moderator today, to introduce the laureate. Professor Li, please.
Ladies and gentlemen, Professor Andrew Chang, I feel very honored here to introduce you Dr. Jean-Luc Chu, the laureate of the Shaw Prize in Astronomy 2018. On my way here to the Shaw College today, as usual, I really enjoyed the view of the Dameidu from here. I guess many of you agree with me that the view of Dameidu from CHK is one of the best views you can get from Hong Kong. If you rush to here today, I suggest you take a look after the lecture today. And to get a better view, you may go to the upper level of the building, find the window facing north, or even better is you go out from this building and go to the deck about 100 meters away from here. You got the best view. So what I just described is actually not too far away from the strategy of cosmologists. So they will travel all the way to the desert in Chile, or even all the way to the South Pole to find the window of the atmosphere through which the cosmic background radiation we're going through and reach the ground. Okay. So, on your way to the deck today, you can also think about, right, how cosmologists is doing the similar things. But even better strategy is like Dr. Chu Jet and colleagues have been trying, is to send the telescope to the space, to well above the atmosphere, so we can get rid of all the effects from the atmosphere. Okay. So it's just like you go outside the building to the deck. Okay. So, and on your way to the deck is one thing you can think about. One thing you can pray about is to pray a good weather, and maybe the air pollution is not as serious to affect your view. Okay? If you got a very bad luck with very serious air pollution, right, cosmologists can always make you feel better, because they always guarantee to get the worst air pollution when they observe the background radiation from the universe. Right? Why is that? Right? To visualize this, imagine that we are living a disk of the Milky Way. The disk is composed of dust grains and gas molecule. So if you are going to observe the cosmic background radiation coming from far, far away outside this disk, inevitably you are going to see the radiation through this dusty disk. Right? So your signal will be contaminated by the dust and the gas within the Milky Way disk. So one thing we should pay attention to today's talk is how is it possible for cosmologists to reveal the underground, the background radiation, which buried under the intensive foreground radiation, the intensive air pollution, which they get from the galactic disk. Okay. And also, most importantly, when they get rid of this contamination, what can we learn from this background radiation about the history of the universe? So I guess you are, just like me, can wait to learn about the story, right? But please just spare me another minute to quickly go through the history, how Dr. Chu Jet achieved all this. So Dr. Chu Jet got the PhD degrees in 1973, and not too long afterwards, he became the deputy director of the Institute of Astrophysics of Paris. And in 1990, he moved to the Institute of Space Astrophysics, started as a deputy director, and in 1998, he became the director of the institute. And significantly of the time of his directorship was devoted to develop a high-frequency instrument for the Planck Space Telescope, which was launched in 2009 and completed its mission in 2013. It's very easy to tell the experiment is very successful by how many prestigious awards have been given to Dr. Chu Jet. Besides the Shaw Prize, earlier this year, he was also awarded the Gruber Prize in Cosmology, and even earlier, the COSPAR Space Science Award, just to name a couple. So it's enough from me, ladies and gentlemen. Let's welcome Dr. Chu Jet.
Thank you very much for this introduction. It's a great pleasure to be here, great pleasure and great honor to present, in fact, the work I did to win the prestigious award, which is the Shaw Prize in Cosmology. I will tell you that among all these years, I've been followed a path which is basically made possible by technology and space technology, which allowed to do things which were fairly obvious in terms of the question we wanted to answer about the universe and the questions and the predictions which were made to that. And so that's what I will describe for that. Let's start in a relatively simple way. You all know that when we look at objects in the solar system, but especially in stars, in the Milky Way, and in galaxies, like the Milky Way, but further away, the light we receive, of course, travel, and it's a few hundred or few thousand of years for the stars in the Milky Way, but it's millions of years and billions of years for the galaxies. And so astronomers looking further and further out have been basically also able to reconstruct the history of galaxies and star formation. That's a big advantage compared to archaeologists. We really see images coming directly to us, and which have been basically freezing the information for many years for our use in reconstructing that. Is it possible to go even further than that and go beyond the galaxy? So in distance, you go at a place where you don't see any more galaxies. And what should be coming from that, if the universe is transparent enough, would be information about the Big Bang, about the beginning of the universe. That was a fairly wild assumption. And the very lucky part is that the universe is transparent enough to have frozen images which come to us and reveal the structure of the Big Bang. Peebles and Partridge in 1967. Jim Peebles, in fact, was the very first laureate of the cosmology, the Shaw Cosmology Prize. And I took many of my goals from his seminal work. And this paper, for example, was trying to describe what would be a measurement of what they call the extragalactic background light, which is basically trying to look at what comes from outside the Milky Way and try to subtract, as the introduction was saying, the emission from the Milky Way. But of course, we see galaxies and point sources. The idea was, should we basically average that and try to get an image of the average of and the light which has been radiated by all stars and all galaxies from the very first formation of these objects. Because conservation of energy is one of the physics principles we cherish. It has never been demonstrated wrong. So this energy should be somewhere. And so that was basically the light of the stars in this cosmic optical background, what we can see by eyes, and a cosmic infrared background, which is the part which has been absorbed by the dust, which was mentioned in the introduction, and re-radiated at longer wavelengths. So that was detecting the CIB. It was a goal of the Kobe satellite. Kobe satellite had, and I will show you that, another goal which was basically to look at the cosmic microwave background, which is the light coming from behind the galaxies from basically the Big Bang, or 300,000 years after the Big Bang, which is still very, very short compared to the 13 billion years. So extragalactic background light is now known from the radio wavelengths all the way to the gamma rays. And that was the dream of some of us, Jim Peebles, for example, but me after. And so you see here the energy inside each of these bands in many decades, from megahertz here, gigahertz, microwave of cell phones, infrared, optical, the stars, and then, of course, the X-rays and the gamma rays coming from the black holes at the center of galaxies. And that's factors of 10. So you can see from the top here to here, almost 8 orders of magnitude. The peak here is the CMB. This is what is coming from the Big Bang directly to us. Stars, light from stars, and reabsorbed and re-radiated here is only 5% of the energy. The Quadrupole satellite was the first satellite exploring the cosmology. You can look here at 1, 2, and 3 microns, so basically infrared, which is just beyond the red light and not accessible to eyes, but you can detect it anyway. And that's the distribution of the stars in the Milky Way. And you can see that if you look at that, it's a very well-defined disk in which we live, the sun being about 2/3 of the radius. The Quadrupole satellite also measured the microwave background. And you could see that basically the microwave background was extremely uniform at 2.7 Kelvin. If you go to the millikelvin, you can see this dipole, hot half and a cold half of the sky, which is just due to the velocity of the Milky Way with respect to this background. So we can measure, in fact, the absolute velocity of the Milky Way. And if you go to microkelvin, then you do see, in fact, what was the fluctuation of the background, which I will spend the second half of my talk onto. The other experiment, so FIRAS was aimed at looking at the energy distribution, and Derby was looking for the cosmic infrared background, which is starlight re-radiated, and so that's what I will describe. Something I will not talk about is that the spectrum of this CMB is very nearly a Planck function, and that's a perfect equilibrium between matter and radiation, which was predicted, and that what convinced everybody that we were really observing that, because astrophysical objects, none of them could bring such a pure Planck function. Come to the problem of separating the galactic dust emission and the cosmic infrared background, because the cosmic infrared background is the radiation of the dust in galaxies, and so you might expect that it's very similar to the one in the Milky Way. And what you are looking for is a shape which is not exactly the same, because the distant galaxies have been re-radiated this energy at the same wavelengths, but it has been redshifted. So you would get more energy in the CIB at long wavelengths than for the galactic dust. The spectrum of galactic dust here is in black. You could see that here. That was a FIRAS measurement in Quadrupole. You could look here at the instrument which was working in detecting the thing in broadband, in the infrared here. And you could see also what was the diffuse emission with bands, which I will rediscuss because that was something which was pretty strange. And you can see the green one, which is typically more extended, and which is, in fact, the CIB. How could we separate that? Well, you need a tracer, because the distribution is not different enough. So we used, in fact, basically a tracer of interstellar gas, mostly hydrogen. And there is a line, a very specific line in the radio, which is a 20-centimeter line, which traces very well this. So you correlate the data of Derby or FIRAS with that. You remove that, which is the black stuff, and then you get to this part here. That's the one we discovered, in fact, in the virus data. This part was much tougher to extract. Just now to give you another closer view on this part, we extrapolated this CIB here to typically something which is 10,000 times smaller than that. So it requires a pretty accurate correlation and subtraction. And that's what I told you. That's 95% of the radiation. So 95% of the radiation we get from outside the Milky Way is from the Big Bang, not from all galaxies and all stars, which was a pretty surprising result. We also got some information. I am not going to discuss that in detail, but we can see basically that it's about 50%. These two are having the same energy. And when we look locally in galaxies, the far infrared to optical average over population of galaxies is typically 0.3, which means that basically at large redshift, when the galaxy formed, the far infrared, which is detected even more in star-forming region, the stars form in clouds, molecular clouds with dust. So basically, the early stars, when they form, do not radiate their optical energy out. It's basically blocked by the cloud within which they form. And there is much more infrared. So earlier in galaxies, this process led to a larger fraction. And so basically integrating more far infrared than optical in the past to typically 1/3 today end up with something which was not predicted because you could not compute that carefully, but it's this 50%. So that's basically very just a bit of history about how did we get the optical background and some of the infrared one. When you look at with a space telescope, the Hubble Space Telescope, you can do very deep surveys and look for galaxies very far away, and you could really make statistics of how luminous are various kind of galaxies and so on. I can integrate that, and you can integrate that as a function of the redshift, the way the lines are shifted, which is due to the expansion, give you a very good estimate of the distance. So you do that, and you extrapolate, basically, what you find. And you could get to a number for which you don't know if you have seen everything, but at least it's a lower limit. So basically, the detected galaxies and converging extrapolation give you this lower limit. How to get an upper limit? Because we might have still missed a lot of energy coming from something we did not expect. Very high energy gamma rays, tera electron volts, 10 to the 12 electron volts, when they propagate through the background, they could, the two photons, come and if the product of their two energies is large enough, they could create a pair of electron and positron. And that's basically slows them down. So there is a cutoff on the high energy gamma rays induced by the background that they have to travel through. And so that gives you a tool to say, knowing where the cutoff is coming from at various energies for the gamma ray, you could describe basically and get an upper limit of the background. If there was more than that, you would not see the cutoff at the right place. So you can see basically that the lower limits are here, and the upper limits from these gamma rays is here. So that's this work has taken probably 10 to 15 years to complete because it's complicated. And for a long time, we were, for example, playing with numbers or estimates which were like that, which means typically a factor of 10. In the far infrared, unfortunately, the telescope which were built, cryogenic telescope, Infrared Space Observatory for ESA, the Spitzer for NASA, when you get to this exercise of integrating all the galaxies you see, that's what you get. In the submillimeter, you get something like that. What we measured was that. So it was obvious that what you detected is just a small fraction, a very small fraction of the galaxies. And that's due to an effect which is when you are at this long wavelength with small telescopes, because cryogenic telescopes were not very big, you don't have a good resolution. So you detect only the very strong ones. I will show you what happened when we use something we call stacking, and I will show you a number of things like that. If you do a detection of a category of objects on the sky, and you look for what are the properties of these at the same place, and you are not enough sensitivity or resolution to get it, what you do is to take the position of these galaxies, for example, and you took the image taken by your telescope at longer wavelengths, and you put them, you center the image on the image that you have detected. The image which were used were the one at 20 microns here for 15 micron for ISO and 24 micron for the Spitzer. 20,000 MIPS galaxies at 24 were stacked together at 70 and 160. That's a 24, and basically you would have see a blurred image here, which is the first image you do. And when summing more and more and more image at 70 micron or 160 micron, you would see that emerge, and the last image would have that. So basically, stacking all these images give you the 70 micron and the 160 that you could not see on the single images. So that basically led to complete, after the fires, to complete basically the infrared part of the CME, of the CME. Okay. Coming back to the dust and the separation of the dust and stars. In the 70s, in fact, we started to look for the diffuse emission of the Milky Way. And we were finding what we expected, which is typically a 20 Kelvin spectrum of dust, which would basically show a cutoff, a Planck function, as the Wien cutoff here. And the stars in the galactic disk were here. So we were expecting a very deep dip here. And in fact, we got basically a dip, which was just typically barely a factor of 10 below that. In fact, when we analyzed the galactic dust, we found exactly the same. We found basically that we measured very well the dust at 20K typically. And then, when we were measuring here with the Derby experiment, we found that. And furthermore, we knew that there was this type of features, which were called the unidentified features. You could see that basically on reflection nebulae, the gas around a star, which would basically have this 3.3, 6.6, 6.2, 7.7, 11.3, and so on. That was these bands. And they were not identified. So we put all that together, and we discovered basically that polycyclic aromatic hydrocarbons, which are basically a piece of graphite, and a very small piece of graphite. Graphite is with hexagon of carbons. So you can make, for example, something which is about 50 atoms of carbon here, which was a coronine, and the first one we looked at. And the black lines are the lines of coronine. And you could see the interstellar line. When you do other molecules, you still find that moving a bit, but everywhere. So basically, we discovered that besides the grains we knew, there was this type of material which were intermediate between molecules and grains, and would basically be heated by a single photon. So we could separate basically that. Knowing the far infrared background, we were interested in looking at its structure, because that would give you information about the distribution of the early galaxies. That's the images we got on the ISO observatory on small field where there was a minimum of interstellar emission. And the fluctuations are quite substantial. You could see basically that the galaxies are gathered. And so the one you can measure individually are a very small fraction of the intensity, where you see it's completely blurred and we say confused. The spectrum of the CIB we got initially here. We compared with what we could do with the Planck telescope, looking at the CIB anisotropies. The Planck telescope was mostly built to look at the microwave, which I will now go to. But it succeeded to do that, and basically check really that basically the anisotropies at the same spectrum as what we did for the diffuse. Coming back to the CMB, so that's the spectrum, and the spectrum, as you can see, the small dots here in the line are the result of the spectrometer of John Mather, who got the Nobel Prize for that, together with Smoot, which detected the anisotropies of this. Let me go to what we did with Planck now. Let's start with the theoretical prediction. Knowing that this background was there, it was predicted that it was there. It was predicted because physicist Gamow and others thought that the helium we see on all stars could have been produced in the Big Bang, and if this has been true, we should have this black body remaining. Which was interesting is that we could, if we could detect that, I will show you that there is a specific behavior of the anisotropies in this radiation, the ripples, on this very uniform thing. The ripples are typically 10,000 smaller than the intensity, so it's very small ripples, which could not be mimicked with the one we detected for galaxies. So it was something very different. So it was, if we would have had the picture I showed you at the beginning of the extragalactic background light from all frequencies, we would have guessed immediately that was something which had nothing to do with the astronomical objects we were seeing. So theoreticians built a model saying that basically the microwave background combined with the evidence for dark matter, there is matter we don't see in galaxies, the rotation curve, or we don't see in clusters, the dispersion of velocity reveals much more mass than the stars. Call that dark matter. And we don't know its nature. That's a big question mark. Furthermore, we discovered also more recently, through the supernovae observation, that the universe is expanding, but instead of slowing down under the effect of gravity, it's reaccelerating. That can be done by a cosmological constant that Einstein showed that you could put in the equation of general relativity. There is no contradiction at all. You could put it something like that. You could also put something which you could call dark energy, a component, which needs to have negative pressure, but then it would give basically an expansion accelerated, and some sort of anti-gravity. Spectrum of the initial primordial fluctuation, what could they be? There was a general argument that they could not diverge either on small scale and large scale, and basically a white noise, random fluctuations, would do that. So the simplest was scale invariant. The small fluctuations at small scale and at large scale would have the same. Gaussian, random, adiabatic. Everything, radiation, matter, everything in the universe is fluctuating in the same way. So these assumptions, in fact, are predicted by the inflation paradigm. The inflation paradigm says the acceleration of the universe is created by something like a cosmological constant or a field which would basically give the expansion. A scalar field would give that. And we don't know what it is either. But it basically implies that basically all these should be predicted with a nearly invariant spectrum. But basically, the large scale and the small scale don't stop to grow under their own weight at the same time. Large scale stop at a different time as small scale. So there would be a slight deviation. So that's a very key prediction for inflation. There was another prediction which was done, is that this fluctuation of density are feeling their own weight, their own attraction. So when the matter is ionized, combined with the pressure of the radiation, they contract, and you see that basically it's going to behave like sound waves. The pressure increases, and then it rebounds, and so you just oscillate like the sound waves that I create and propagate to you. Simple physics, classical physics, well known, which tells you that the small scale fluctuation have contract and rebound several times. But there is one which is large enough, so it contracted just in the age of the universe. At the time, hydrogen would recombine. Then, no more connection between the electron and the photon, so the image is the one we see. It propagates freely, basically, through the universe. And the oscillation stops. So what we see is a frozen image 300,000 years after the Big Bang, when the plasma became neutral and hydrogen became neutral. And so in this frozen image, you will have the one which has contracted once, the one which have rebound, the one which has contracted twice, and so on. So it would do basically a set of proper modes, like you would do for a music instrument with wind. Same thing. It has specific notes that you can do, which depends on the length. So that was predicted. And so the other thing which was predicted was that basically the intensity would show peaks if you look at the various scales. But the polarization will also show that. Why? Because the contraction induces a velocity, and this velocity would basically make you, if you are falling with the matter and the radiation, before the reionization, if you were falling with the matter, you would see basically what's around you converging, what's beyond, in front of you going faster because it has accelerated more, what's behind you would have been less. Well, that's called a quadrupole. You expect basically one direction to have weaker intensity than what you see. When you get something like that, around you, a strong radiation with both polarization, and here the radial radiation you're falling into. When you scatter this light, you basically would get a polarization. So there is a polarization which is induced by the velocity field in this oscillation, which is very well defined too. And that would give you either that or that, depending on where you are in these oscillations. You could also have another type of perturbation, which is gravitational waves, that I'm not going to discuss here. But these ones have been used and have been seen very well. That's an example of stacking. Take the temperature map, look at the peak, and look around the peak if you see what I was telling you. The polarization is indicated here by that. And depending if it's contracting or expanding, you would have positive or negative Q polarization. The U polarization will be basically the 145 degrees off. So you see, basically, when you stack also many thousand of peaks in the intensity map, what you see is a negative Q, polarization is around, then another ring where it's radial. And of course, for you, 45 degrees, you don't see anything. That's the Planck data. In fact, it has been detected for the first time with WMAP. The WMAP had not sensitivity, which was orders of magnitude smaller, but you could see the detection of that, the red one and barely the negative one. And just to tell you that if you simulate that on a computer and look at the Planck data, and you can stack the peaks or the minimum. One is the Planck data, and one is the simulation. And I think the Planck data is that, and the simulation is that, because we can see some noise here. So it's not what we use to analyze the cosmology, but this image say, well, the physics we believe we have described is there. The peaks where we look for, and in 1995, many experiments were looking for this first peak, and as you could see, it was not detected. You look at, well, not detected. The EMR experiment of George Smoot was that, but it could not detect the first peak because it was too large scale beam. 3 balloon experiments, Boomerang Maxima, detected the first peak, and Archeops, which was basically an early version of the HFI Planck instrument, detected the bridge. That's the orange one. So that's the first peak, the one structure which has contracted once only. Second peak is here, and I'll show you now. WMAP, of course, got a much better image than the balloon experiments. That's the intensity, and that's the polarization. And what is plotted here is more or less, it's a power spectrum, but more or less, it's the amplitude of these waves, these ripples, as a function of the angles. Typically, 1 degree on the sky here is the first peak. That's the region which has basically maximum compression. And then you detect very well the second one and barely the other one. And you detect basically one of these peaks for that. And basically something which could have been one which is predicted reionization and which revealed, as I will show later, an artifact. Just look at the image. So that was the resolution, which was COBE and the sensitivity. That's WMAP. So COBE, WMAP, Planck. So you could see more resolution and a much higher signal to noise. What we did was, during the development of the instrument, we published what we call the Blue Book, which was basically predicting what we could measure. So we took one model and basically ran that through a simulation, and you could see that the simulated data on the model we had put in, the red curve here. That's the 2018 Planck measurement with the best model and the Planck data. We detected, I think, 7 or 8 peaks. And with an accuracy of typically 1% on the parameter. So we have been going through refining the model, but the basic model was what I briefly described, but improving the accuracy basically didn't break the model. Planck Satellite, artist view. By the way, on the slide you showed, it was NASA. NASA contributed pretty much to the Planck Satellite, but it was European Space Agency, so don't show that slide to the Director of Science of ESA. In this image, you see the Earth, the Sun, the Moon orbit is 1/3 of the distance there. So basically everything which is warm is in the back. And so basically you cool here a telescope at 35 Kelvin. Then the instrument, which is there, get to much cooler. The Planck satellite is really a gas factory in the sense of, we say a gas factory is something so complicated and so on. And, there is 3 active coolers, one to 18K, one to 4K, and the other one which basically goes to 0.1K. And these screens here are the one which basically screens from the solar panel, which are 300 degrees centigrade. So you could burn pretty badly your hand if you put it on that, if it was in space. And knowing that the detector here are 0.1 Kelvin. So I'm not going to describe all of that, but basically that was a pretty complicated system, and that was the biggest challenge of Planck. And people asked me yesterday what was one of my greatest rejoice or joy. It was first when we launched and the cryogenic system worked perfectly. We predicted that it would cool down all the way to 0.1K in 45 days, and it was 47 days. So this machine was very well. So that's the maps. And the map we get out of that are frequency maps. For the low frequency instrument, radio detection, 30, 44, 70. The 6 frequencies for the HFI. And when you look at that, the images are the same, including for the low frequency instrument, which had more than 10 times more noise, but on such images, you would not see any difference, or any difference with the WMAP at the same frequency. Polarization, we got the polarization, Q, U, and the sum of the square of the two, which is the degree of polarization. So that's what we used for that. Question, which was raised in the introduction, how we do that? Well, we do that because we had tracers of interstellar medium, the H1 line at 21 centimeters, for example, and because here, as a fraction of frequency, the dust foreground is here, and we get basically, for example, synchrotron. So for polarization, there is only the dust and synchrotron, and the CMB polarization is here. So you can see that basically it's difficult, but the CMB is not way down the high latitude. And even for the intensity, the CMB dominates in this range of frequencies. So we do this exercise of component separation, and basically that's what leads to what we use to do the cosmology. So now, that's power spectra, and I'm not going to cut your maps into spherical harmonics for one who understand that for decomposition on a sphere, and it's basically equivalent to do Fourier transform. It's basically spatial frequency in angle, and so that's basically the equivalent of the K number for a plane on the sphere. 1 degree is here, and 5 arc minutes is somewhere here, which is the resolution of Planck. So it's basically as a function of the spatial frequency, or of the angle, if you want, which is easier, the intensity, and the E modes, the one I showed you, which were the one which were either radial or poloidal, not at 45 degrees. And so you can see basically that we can decompose that and really extract the CMB. We can do more than that. When I told you that the universe is transparent, but when it propagates through the big structure, the large-scale structure, the protoclusters of galaxies and so on, there is a deviation, of course. Light is sensitive to what general relativity says, but it's known from 1919, 1 century ago, we checked. Eddington and his collaborators in an expedition on a solar eclipse in South America detected the deviation of the stellar light of stars which were close to the sun image during an eclipse, and demonstrated that the light is deviated by gravity fields. So the CMB photons are moving basically with wiggles, just related to the change of the gravity field. That's a simulation, and that's the type of motion. So you can see the small displacement on the temperature, on the so-called E modes, which are the one, and the B modes are the one which would be created in the early universe by gravitational waves. That's the goal for the next generation. But you see that furthermore, for example, we will have to get rid of the effect, what we call the lensing, the deviation of that, will transform some of that into that, which would mimic gravitational waves. So we would have to get rid of that and of the B modes from the dust before we get to the gravitational waves. Another example of stacking on the lensing. I told you that the CIB, cosmic infrared background, is better tracer we have of galaxies at large redshift. If you stack the displacement that you, so we can measure this displacement in Planck. It's basically doing 4-point correlation functions, and there are mathematical ways to do that. So this displacement is measured. So you stack the displacement measured on the peaks of the CIB. That's it. You would do the same, the displacement on the minimum. And you'd see basically that where there is less infrared and less galaxies in the past integrated, then basically you see a divergence. And if you do random stacking, that's the displacement you see. So basically, that's the image of the displacement on the galaxies as measured on the CIB. These galaxies we don't see by individually. I keep that. So what we used for the polarization is the CMB intensity with these peaks, the E modes here, the correlation between T and E, the same physics is building its velocity associated with the oscillation. And so you can reconstruct from the lensing the spectrum also of the fluctuation of the gravity, the potential of gravity. To measure the cosmological parameters, there is, as predicted by the theoreticians, these acoustic peaks are extremely powerful. Nevertheless, you could not determine the 6 parameters which have to be determined for the model. If you look, for example, for the lambda is the cosmological constant or field you need to account for the acceleration, the reacceleration of the universe, and that's the matter quantity. And if these two, the sum is 1, it's a very specific case in which, in fact, we happen to be living in, which is that although light does not propagate in straight line when they go in clusters of galaxies, on large scale in the universe, they do. The geometry is large scale, at very large scale, is Euclidean. Cosmologists have always said, ooh, if we are close to that, why aren't we exactly at that? So, if you want to add one, if you use only the acoustic peaks, you want to add a measurement. And so, for example, WMAT used the H0, the Hubble constant, the speed of the expansion, measured by the Hubble Space Telescope. And so, depending on the H0 you put, you can see basically that you are not, it's not degenerate. It's almost degenerate, but it's not. But you need something else. You cannot prove that we are really exactly on that. Now, just using the CMB data, but using the lensing, you would get from this uncertainty to the blue, the dark blue here. And if you use something which is different, which is the baryon acoustic oscillation, which is in the galaxy field, you can look at the velocity which have been left by these oscillations. And we detected them very well. And so if you add that, and that's one, if you add lensing and BAO, the parameters shrink in error bars around basically the values we have, which is very impressive because it's very independent measurements. And so that would give you that, which is bingo on the line. So the parameters here are, I don't want for you to look at these numbers and retain them. What you would see if you would look at that carefully is that basically most of them, except this one, are better than 1% accuracy. I'm also an astrophysicist, an astronomer, and when I worked on the interstellar medium, I can tell you that when we were 10% accurate, we were pretty happy. And then, so these 6 parameters is the baryon quantities, the cold matter, cold dark matter, that we don't know what it is, but we know exactly what amount is there. The amplitude of the initial fluctuation, that we don't know exactly the physics of inflation, we cannot do that. And NS, which is just 1 for the purely random fluctuation. And the deviation, which is predicted by the simplest model of inflation, are typically 4% deviation of the scale invariance. And that's 0.965 here. Okay, so image of the polarization, whole sky. That's an image which was really only obtained by Planck. WMAP had measured it, but as you saw, with much lower signal to noise. When you take a 10 degree by 10 degree, you can see basically what you find, and that's smoothed now, the small square. We can, in fact, also look at the 350 gigahertz, which is far in the cutoff of the Planck function, and which is dominated by the dust. And so the dust is aligned in the magnetic field, of the galactic magnetic field. And so that's basically a map, full sky map of the orientation of the galactic magnetic field. You could see, for example, interesting things for galactic physics. You see that the field lines like that do something like that. That's basically the so-called chimneys around, above the galactic disk of big region of star formation and blowing gas out and pulling the magnetic field from it. If we use only the temperature, that's the model you get. If you use the temperature and the polarization, basically that's the fraction of sigma of the error bars. Basically, there is absolutely no deviation whatsoever. So it's even annoying that in this model, standard model of cosmology, there are two big pieces. We don't know the physical nature. People have looked at an accelerator trying to get a particle which would be the dark matter. Neutrinos were a guess, which was not right. And so, nevertheless, with general relativity, you build a model with all these properties, and you observe. I show again the model, the best model. It's the best model extracted from the temperature. That's the data. Remember that this is the degree scale. This is typically 5 arc minutes. And this is the residuals. And this is plus or minus 1 standard deviation. You take this model, predict the polarization. That's the E mode. Sorry, yeah, that's the E mode, and that's the TE correlation, and that's the data. The blue line is not a fit to the polarization data. It is the model given by the temperature. So this, of course, is the same physics. It just says that the physics I described anti-waving to you is the right one. And it's classical physics, so the ingredients seems to be the right one. In the last set of papers we published typically a few months ago, that's basically some of the parameters from pre-WMAP, WMAP 1 to 9, that's in number of years of integration, Planck 2013, Planck 2015, Planck 2018. From WMAP 3, basically everything is within the estimated error bars. They are much smaller for the last version. But basically, the analysis has been relatively well done, even at the accuracy of the WMAP, except one point, but you are never much more than 1.5 sigma away. Let me just tell you one thing. One parameter is the reionization parameter. What is that? The universe is ionized when it's very hot. I told you that 300,000 years after the Big Bang, it became neutral, transparent. Well, when the galaxy is formed, there was UV, X-rays, and so on. So it's reionized. The optical depth, if you measure it to the more distant quasars, is typically 5%, a little less than 5%, between 4.5 and 5. So it's very interesting. First of all, this parameter tau, which is the Thomson optical depth, up to reionization. And reionization, we don't know when it took place. We know the more distant galaxies and quasars, but we don't know if some of the things, or astronomers have been talking about population 3, population of stars, which would be forming before galaxies form, for example, which would be at higher redshift. So this parameter now, that's the one, WMAP1, put at 0.17. Then it went to 0.1. In 2015, with a low frequency instrument of Planck, it was determined to be 0.08. And finally, when we thought we were sure that we had removed all systematic effects for the high frequency instrument, which is 20 times more sensitive, we got a number which is 0.056. That's pretty close to what the more distant quasars are giving. So there is not much reionization beyond that. So that's an interesting parameter. It's not, the accuracy is not even at the 10% level. It's at, I think 15%. Gravitational waves. Gravitational waves are generated in inflation. You do an inflation model. You have this quantum fluctuation of the field, which would generate gravitational waves. How much? Well, model of inflation is counted by the 100 in the literature from the last 10 years. And it gives very, very different predictions. So there is not a specific. Nevertheless, we can put an upper limit. The upper limit that Planck alone can put is was not very good, 0.3 or something like that. That's a ratio of gravitational wave with respect to the density fluctuations that we have all been describing. I've been describing only the energy density fluctuation. So the BICEP team thought that they had detected it, and unfortunately what they had detected was the dust part. So in combination on BICEP2 and Planck, we transformed their hope to have detected the primordial gravitational wave to an upper limit, which is typically the best available today, and which I told you will be the next generation thing. So I will finish on inflation. Inflation predictions are where we touch really the very, very beginning of the universe. What has accelerated the universe to the expanding universe we know, and which slowed down for a long time until its reacceleration, which is based on probably something similar to inflation. So it predicts that the universe is flat, because in this accelerated expansion, even if the geometry is not perfectly Euclidean, you go towards Euclidean. When the Big Bang, classical Big Bang phase, when it slows down, it's the other way around. You go away from Euclidean. So you need, but basically, inflation had been such a number of decades, a huge number of decades expansion. You predict basically that the flatness at very large scale should be very good. Well, that's omega k is with respect to the one of the sum of the cosmological constant and matter I was telling you about at the very beginning. If there is a curvature, we can solve the model including a curvature. That's what we find. Nearly scale invariant with typically a 4% effect due to the scale. NS is 3.3 plus or minus 0.004. Well, bingo. Almost a power law, we just look at the derivative of that, which is just a slope, and basically we find to 0, or we don't know, and non-Gaussianity and adiabatic. So the generic prediction of inflation, except one, typically the prediction is there is gravitational waves. There is no generic prediction. So what is done now and will be done in the future is to look at the NS, this tilt, because that depends on the specific model of inflation, and the tensor to scalar ratio, the gravitational wave. And so that's the upper limit of Planck in this plane. That ruled out several hundred models of inflation. But there are about as many left, so job is not done. Okay, so that's the future experiments. Last thing, tension. The Hubble constant is measured by the supernovae grand distance and the Hubble Space Telescope. And it gives a number which is 73, 74, with this type of error bars, 1 standard deviation, 2 standard deviation. Planck gives something which is 66 point something. That's the quantity of matter. And so, basically, Planck constrains the matter density. This measurement do not, but give a Hubble constant, which is 3.5 standard deviation away, which is very small probability if it's just due to noise. That's the point, and you have to be careful. 19th century, some people said, oh, physics is almost over. There was just one small problem which led to quantum mechanics and led to general relativity. So that's the interesting point where this new physics, because it's new physics, both the acceleration, the field which accelerates, or the cosmological constant, is new physics. Dark matter is new physics. And we have very little, comparing with the model, the Planck accuracy with the BAO, and so on. So finishing with that, I will show you the Planck data is now, when you combine with the South Pole telescope and ACT and BICEP and so on, you get either things here, but also high angular resolution. So that's the beginning of the next phase. So I'll stop on that and say that the work is not over. So thank you for your attention.
Thank you, Dr. Pouchet. Please take a seat at the center of the stage for the question and answer session. Will Professor Lee please join Dr. Pouchet on stage and moderate the session?
Okay, thanks a lot for the stimulating talk. So first, let me apologize for my misleading introductory slide. I was tricked by NASA.
No problem.
Let me emphasize that Planck is a project led by ESA, but I happen to use artwork that NASA claimed the credit, just artwork. Okay, any questions? Must have lots of questions for this challenge talk, right? Okay, please.
My name is Michael. I'm an engineer, so I don't know much. But when I was young, I was thinking about this kind of spacing in the sky is really intriguing. But I can only capture very little of what you said. Maybe I can ask something very fundamental, if that's okay with you. Those are fundamental physics, for example, like using the light to measure things. There was a fundamental assumption. I think Einstein started with this basic assumption that the speed of the light is constant. And from that, he derived a lot of intriguing theory. And even today, as you pointed out, that his theory was observed just 100 years after his paper was published. You know, those are relativity theory kind of thing. So I was just wondering, this kind of very bold assumption, even though throughout the year nobody denied things like the light of the speed of the light is constant, those kind of things. Is it we take it as like 1 + 1 = 2, that kind of fundamental assumption, or is it based on some very fundamental thing that the physicists will think this is very important, or even you can intuitively verify that? And this is just one simple assumption. Is there any other major assumption about the universe? I know the Big Bang theory was also verified in some way, but some very general physics kind of thing to arouse us about the interest in the sky will be very intriguing to us. Thank you.
Yeah, thank you for this question. The reason for which making models of the universe, which could be infinite, was not possible before general relativity, because in Newtonian gravity, I'm taking a point of view of the observer. A theoretical physicist would not answer your question in the same way I'll do, but I will not try to reproduce their argument for having at least one speed limit in physics that cannot be exceeded. But I'm telling you that if you would not have that, a model of the universe which would be either infinite or very big, and I will come back to that because I didn't say that, but that's one thing we learn now about the size of the universe, that it's much bigger than the one we see, which is already pretty big. And I will come back to that. If you would interact with everything at the same time. If you would put this limit to infinity, everything will interact with everything immediately. So basically, you would collapse, the universe would collapse in 0 time. So the existence of a universe which is even expanding, or it was slowing down, but it's expanding in a decelerated and a reaccelerated fashion, requires an upper limit to interactions. We receive the information, as we do, from 300,000 years after the Big Bang, which is when the light is coming to us. But the information is coming to us from much earlier time in sound wave. So it's not, the information we know about the Big Bang is not limited at 300,000 times. It's reflecting something which was just propagating through the sound waves. And we go, as I hope demonstrated to you, we go very far to that. So, and this information is piled up, and it's coming to us. So for example, if you would wait 1 billion years, we would see basically a layer of the universe, which is behind, which is certainly not very different from the one we see statistically, because the universe is almost Euclidean, and so if it has any curvature, which would give, for example, a limited size, the size is much bigger. The omega k is less than 10⁻�3. So basically, order of magnitude, the universe would expand is similar, 1,000 times more than what we observe. And we don't see any interaction with that. And it's lucky for us. We would not be here if it would be that way, because the universe would have collapsed in 1 quantum time. So that's my view in terms of an observer thinking about physics, a physics which would not have. Now, velocity of light and of zero particle is considered as that, and all the physics, much of the physics is based on that. The very interesting point which appeared with the detection of the gravitational wave, and the fact that the gravitational wave, not from the black holes, but the one from the two neutron stars, they detected with a gamma ray burst, X-ray burst, and so on, proved that the gravitational waves propagated also. So gravity does propagate at the velocity of light within 1%, I think, or something like that, which is a major step, because that was not known. So gravity is also propagating at that velocity. Thus, there is this wall at 13.8 billion light years. But it's not a wall. It's just, if we wait, we will just see behind. And so we do not see any evidence of interaction beyond that. Thus, there is a finite time, a finite velocity.
Great. Any further questions? Yes, please.
Hello. I'm doing some kind of this research. So as I know, there's some mystery about the star formation, the mechanism about star formation. So as I know, the most mystery part of star formation is that some turbulence problem or the magnetic field problem inside the formation of star inside some filaments. So,
sorry.
So,
I was for you that.
My question is that, is this possible, or can we using the CIB to understand or to do some kind of research or to understand about the problem of star formation, the mechanism of star formation inside the filaments, inside the giant molecular cloud? Thank you.
Yes, that's a very interesting path to follow on the Planck data, because we never got before such a good picture of the magnetic field inside the interstellar medium. Now, as you probably know, star formation in molecular clouds and in interstellar gas is not fully understood by far. It's not even, there is not a full theory of that. There is another part which is even less known. When the objects formed in this, what I described, the smaller structure, smaller than galaxies, would basically also contract, and if they cool, and they would cool through hydrogen lines and helium lines, we learned that basically they would virialize, but basically if they cool, they would collapse. And at large redshift, 30 or something like that, masses of the order of 10 to the 7, 10 to the 8 solar masses would collapse. That, and they would probably fragment in very massive stars, because there is no heavy elements, no heavier than helium and lithium. So this population is that what people call population 3. We don't see any evidence of that. It doesn't mean that it does not happen. It probably, if it happened, it stopped itself by basically reionizing the medium and so on. We don't know. We have also put now strong limits on the extra realization at high redshift beyond the most distant galaxies we see at redshift 10 now. So that's a puzzle, which is, and the idea that it could be the turbulence could play a role is obvious, because the velocity at which this thing will collapse will certainly induce turbulence. Not exactly the same as interstellar medium, because it will be warmer. So information about clouds and what you said, filaments and so on, is certainly present in the Planck data, and people are working on that. Whatever it can be said on this pre-galactic star formation depends very critically when the magnetic fields appeared, pre-galactic or not. And so we worked with some colleagues on that, and we cannot say much about it. But so that's a branching which would be one branch of your question. But,
thank you.
Well, that was a very creative questions. It's exactly what we were looking for. Questions from students.
Don't hesitate to ask questions if you really don't understand something I said, because I said many things.
Thank you. My name is Dominic. I'm trained as an engineer, so I'm afraid I didn't understand a lot of the thing that you presented. But although my favorite program is indeed Big Bang Theory, this is a TV program. Now, see, here comes the question: is we always know all these background radiation about the microwave and the infrared. It seems like the evidence which help and suggest about Big Bang Theory, and that would put the universe at about what 4 billion years old. My question is, how does that conflict between religious and science? Because now we have evidence that says the universe is 4 billion years old, whereas the Bible would say it's about 10,000 years old. How do you resolve that personally? Do you have a conflict between science and religion?
First of all, I don't have a religion, so I don't have a problem with that. I still can ask myself a philosophical question, let's say. So, but the age of the Earth or the age of the Sun was asked, and the energy of the stars was not known. So before the 20th century, that was a puzzle. It was obvious that the sun, if it was combustion of something, or if it was the gravity, if the sun was contracting to get its energy and so on, that could not make it live as long as the Earth and at least the evidence we have on rocks and so on of the age of the Earth. So the fact that it's nuclear fusion, which was proven basically by the fact that we detected the neutrinos, which are from the reactions in the sun, give you and give us a model for stars, which also in the 60s, when I started to learn cosmology, led to a puzzle that the age of the universe, which was computed at that time, was somewhat smaller, not very small, but somewhat smaller than the age of the oldest stars. Now, the model we have now resolves that contradiction, for example, which was pretty severe. I mean, having stars older than the universe was uncomfortable for cosmologists. So that's why we are looking so hard to find flaws in this. I can tell you, we really looked for it. And so far, except for the Hubble constant, so we didn't find anything. So my belief is that the reasoning we are doing, giving these numbers, there is so many things which it's an ensemble of observations which are the nuclear physics, the particle physics, the astronomy and cosmology observations and so on. And that fits up to the point where we don't know what's dark matter or dark energy is. So that's where the puzzle is for me. But basically, I follow the path of 17th century philosophers, which they said we should look at nature and not try to find in us the answer about nature and the universe.
Please.
So hello, Dr. Chu Jet. I'm a physics student, but I haven't heard a lot about. I'm here, up here.
Over there, upper left. In the middle.
Yeah. So I have heard some research about CMB, but it's the first time I have heard about CIB and COB. So forgive my ignorance in that. I would like to know, like, as this is as a rise of multi-messenger astronomy, so we can see different phenomena from different wavelengths of the EM waves. So what do you think that is the most special thing we can see from the CIB and the COB that we can't do in other wavelengths, or something very interesting you find in these two specific wavelengths?
What some of my younger colleagues have done, Hervé Doll, who has done the stacking, but Guylaine Lagache, who has been building models for infrared galaxies and trying to see if the other part of the model of galaxy evolution fit with the CIB. It fits, and it's not very accurate. The development of the model of evolution of galaxies is pending on being able to say what is the star formation rate? What is controlling star formation? Star formation was studied even when I started to work on astrophysics in the late 60s. People said, we have gas at a given temperature, and we look for instabilities. That's a very well-known, and we know how to treat this problem in physics. We had already some evidence about the temperature of the gas through line molecules and so on. And the answer was that these cold clouds that we see in the galaxy should collapse in one free-fall time, which was typically 1 million years, or something like that. And the evidence we have in terms of the output in radiation is that the turnover of gas into stars is billion years. That was what was discovered after, and that was related to one of the previous questions, is that it's not the gas pressure which dominates in the interstellar medium. The velocities we observe in the interstellar medium are way supersonic, Mach 20 or 30. But they are subalvinic. Alvinic meaning sub-alvane velocity, which is basically the one for which the pressure is made by the magnetic field. Magnetic field has the energy density, which is comparable to rho v squared, the density times the dispersion velocity. So in fact, we know now that the magnetic field, the wave and the dispersion and the turbulence, the MHD turbulence, is what's there. Now it's very homogeneous. So we don't have a model. There are big numerical models which kind of mimic what's happening, but nothing which can give us a model, a really physical model where you can say with uncertainties what it predicts for the evolution of galaxies. Thus, the CIB is telling us now something which is allows the answer. It's compatible with what we understand of star formation. And there is no contradiction. It doesn't push too much upwards or downwards, because what we do is empirical models. So you put an empirical model of star formation and you find basically that it works. What is interesting is that we could say that in the CIB there is not much else than what we could predict on this empirical determination. It's not the same as doing the physics of the CMB and so on. Cosmologists have an advantage. Cosmology is very simple compared to star formation, which is even simple compared to biology and an origin of life, which is probably simple before origin of conscience. So in origins, which are philosophical questions, I am interested too. I could have answered that to one of the questions. I didn't choose. I was attracted to that, and I didn't choose for that. But now I'm happy I choose the simplest one. So the one you ask is still too complicated for what we know.
Okay, thank you anyway.
Okay, top in the middle.
Oh. Yeah.
I'm interested to know if we can see differences in sort of the third dimension yet, in terms of if we look at the same spot in the sky from 2010, 2015, 2018, do we see the cosmic background change, or do we not have that resolution yet?
No. That's, yeah, we have all look at the numbers and so on, and no, that's much too small. You could, right, the CMB is propagating through galaxies. So, for example, we checked, it's not an answer to your question, but we checked that the cosmic microwave background has a higher temperature when you look redshift 1 galaxy and you look at the lines excited, molecular lines excitation. There is molecular lines, CN, for example, which were the first measurement on the top of the microwave background before it could be measured by COBE. So you measure these lines, which are not excited by collision, they are really, and you find basically that the background goes as 1 plus z. So you could see the influence of the cosmic background in redshift, for example. But when it was produced, and what you are talking about is basically the layer. This layer is thin, but thin, it's at a redshift of 1100, and basically the thickness of the recombination is pretty fast, but it's 50. So it's something which gives you a layer. It's basically except for the very smallest structure, you do a cut, a spherical cut, and the change are much slower than reasonable observing time.
Thank you.
Okay, due to the time limitation, we can only receive one more questions. Who want to get the last one? Okay, please.
Hi, I'm Harris, and I'm a high school student. And although perhaps I didn't understand most of your ideas, but in fact that makes me more wanting to study your ideas in the future, to understand them. And my question is, since astronomy is on the decline and not many young people like astronomy anymore, my question is, how will you suggest us to promote this beautiful science to the next generation?
First of all, I'm not sure that astronomy, some part of astronomy are on the decline. Other parts, not talking about cosmology, but one which is really rising fast is exoplanets and solar, planetary systems formation, which is, as I was saying, in this big philosophical question of origins and so on, is becoming really quite interesting. And looking for any kind of sign of biology external to the Earth would also. So I think it's astronomy as it was in the middle of the 20th century is in the decline, but there is new topics which are rising. So I think we should encourage people to come to astronomy to develop these.
That's exactly one of the motivations of the Shaw Prize, and I think it worked quite effectively. Look how many young faces we're having here. Okay, so you're more than welcome to stay for longer to ask more questions, but off the stage. So we have to thank Dr. Puget again for the stimulating talk today.
Thanks to you to be here.
Thank you, Dr. Puget and Professor Lee. Please stay for a moment. May I invite Professor Rocky Chun, Vice Chancellor of CUHK, and Professor Andrew Chan, Head of Shaw College, to present the souvenirs. Professor Chun and Professor Chan, please. May I first invite Dr. Puget? Professor Li Huabai, our moderator. Thank you very much. This is the end of the lecture. Thank you for joining us today and have a great evening.